Hi, good day. Tour guide Mike back, and I'll be talking about the important concept of even and odd functions. Knowing about even and odd functions is useful in differentiation. It can give you some clues if you're getting the right answer or not. Also can be time saving in graphing, and we'll explain that a little bit. But our main reason is integration. It can be really vital in integration. It can save a lot. Sometimes you can just inspect an integral and know that it's zero or know that it's some number just by knowing these properties. And so our goal is to build up some knowledge about it. So I've drawn an even function here, and I'll ask you, what do you notice about it?
Looks like an upside down McDonald's sign, but maybe symmetry?
Yeah, like even and odd are both types of symmetry. And you could answer this question in two ways. What do you notice about it from the graph? And what that would be is it looks like a reflection in the y-axis. So if we take any point here and look at the x point, corresponding x point, if we go over the same amount negative, then the value, the height should be the same. Okay, so what we notice from the graph immediately is that it looks like a reflection in the y-axis. Okay, but we could go on and say, well, okay, from actual equation or from the graph, what does this mean? Okay, so what will this look like? What will this mean? Well, it means if we look at f of, say, -1, take a value. So -1 is here. So we have -1 here. So f of -1. Okay, so that value there is equal to -1. Okay, but then if we look equal distance over here at 1, it has the same value. So f of -1 is -1, which is f of 1. If we look at the root or 0, the one here at minus the square root of 2, and it's impossible to tell that's exactly minus square root of 2, but I know it is. Since it's a root, it's equal to 0. And then if we go the same distance over here in the positive direction, then it also is a 0. So f of minus square root of 2 is equal to 0, which is equal to f of the square root of 2. And we can pick one more point. So let's look at the point -1/2. So if we look at 1/2, so that's halfway through here. It's around here somewhere. You look at that value. And I'm an expert at reading these graphs, so I know that it's -7/16, so f of -1/2. No, the real reason why I know it is I know the equation for this actual graph. So that's -7/16, and that's the same value as f of 1/2. So 1/2, and this is a -1/2. Okay, and more generally, what we would have is if we went on and exhausted all the points, we would have f at -x is equal to f of x for all x in the domain. Okay, so this is how we define this notion of evenness. So a function is even if f of -x is equal to f of x for all x in the domain. Now, implicit in this definition here is that it must satisfy if x is in the domain, then -x is in the domain, and vice versa. So this is a necessary precondition to consider evenness. Perhaps you have to restrict the domain such that this is true and just sort of consider evenness of part of a function. Well, this evenness is nice, as I was mentioning. It can help with graphing. So what you can do, for example, is you could just carefully graph out this left side, say, and then just reflect it in the y-axis and mimic what you did on the right-hand side. So you could graph one side, either left or the right, and then just copy it over in a mirror way. Okay, so getting back to the mystery why I knew those exact values is because This is actually the graph of the function f of x is equal to x to the fourth minus 2x squared. So just as I asked you, what do you notice about the graph? What do you notice about the equation of the graph?
Well, it looks like it's a polynomial, so perhaps polynomials means even functions?
Well, it is a polynomial, yes, but there are even, odd, and mixture polynomials. The real thing to notice is, well, what we can do is we could rewrite this x to the fourth as x squared all squared. And then we notice that it's a function of x squared. So it's x squared squared minus 2x squared, hence a function of x squared. So the real thing to notice is it's a function of x squared, not just of x, but of x squared. And this is always true. There's a small mistake here, so cross that out. So a function is even from its domain to the real line if and only if it can be written as a function of x squared. So let's just go through this. Not that this is a course on proof, but this proof is so simple and nice and will be done in a flash that we may as well do it. So the first thing to notice is that the absolute value of a number, x, is obtained by squaring it and then taking the square root. So if you started with minus 3, you square it, you get 9. Take the square root, you get 3. Hence, it returns the absolute value. So in noticing that, then the statement that f is even, well, we know that that's a statement that f of minus x is equal to f of x, but that's the same thing as saying f of x is equal to f of the absolute value of x. Why is that? Well, f of the absolute value of x is equal to two things. It's either equal to f of x or it's equal to f of minus x. So that's what this f of the absolute value of x is equal to. It's one of these two things. And if it's even, and these are the same value, they're both equal to f of x. So going backwards from right to left, we see that this must be true. But then this absolute value of x, we can just substitute in this formula we have. And so this is equal to then f of the square root of x squared. Hence, it's a function of x squared. But in the process, going just from this step here, we also see that it's a function of the absolute value of x. So hence, we have the following fact. F is even if and only if it's a function of x squared, or if and only if it's a function of the absolute value of x. Let's use it. Here's a simple example. Is the absolute value of x cubed even?
No, because x to the power of 3 is not a mirror image about the y-axis.
Actually, that's a good question, but it would be, actually, if you take a look at it, because of the fact you're taking the absolute value. You take x cubed, it looks something like this, but then, because we're taking absolute value, all these negatives, they become positives, and so you'll get something that looks like that, and this won't appear. And it will look like a mirror image, and this is even, so the answer is yes. And the easiest way to deduce it, you don't need to graph it, is just write out. So the absolute value of x cubed, well, that's equal to the absolute value of x times x times x. But absolute values, the absolute value of a product is a product of the absolute values. So you can deduce this, but just take some examples and you'll see it's clearly true if you don't know this fact already. And so then the absolute value of x cubed is equal to the absolute value of x times the absolute value of x times the absolute value of x, which is equal to the absolute value of x cubed. So it's a function of absolute value of x. So it is also a function of x squared. So it is even. Another question a lot of students ask is, why do we call this property even? So even doesn't sound like reflection. So why is this called even? And also, does it have anything to do with even numbers? And indeed it does. And this is one of the ways that we can remember this. And the answer really is through polynomials. So polynomials with only even powers are even. So here's an example. 3x to the 6, that's the power of 6, it's even. Plus 2x to the 4, 4 is even. X squared, 2 is even. Plus 4, which is really x to the 0. 4 times x to the 0. X to the 0 is 1, but 0 is also even. So polynomials with even powers are even. Polynomials with an odd power are not even, as we'll explain later. Let's look at a little bit more interesting example. Cosine. Is cosine even? Well, remember the reflection idea. So if we take a value here, so let's take the value of minus 5. So that should, if we reflect it in the y-axis, then we get the value, we look at x of 5, and this should give us the same value. It does. Let's take another example. Let's take the example of 2. So 2, we'd be right about here. So if we look at minus 2, does this give us the same value? So by inspection, it looks like it is even, and one could verify, yes, that this is always true. Cos of minus x is equal to cos x for all x greater than 0. So yes, it's even. Notice we only had to consider x greater than 0 because if x is greater than 0, then minus x is less than 0. So we're considering all values either on the left or the right, which is all you really need. All right, here's an interesting thing to ponder. Here we have this cosine, and let's reflect about how cosine was defined. Cosine was defined as the x value that you obtain as you travel around the unit circle counterclockwise, starting from the point 1, 0. It has absolutely nothing to do with polynomials by its definition. Yet, we just said that this is even, so we just established that it's even. So by the above result, cosine of x is some mysterious function of x squared. So what type of function could it be of x squared? And we will not answer that right away. In fact, it will probably await your next calculus course when you take a look at Taylor series.